Hello and welcome back to another plane geometry video. I think it's safe to say that we all have an intuition about what points and lines and angles are because we know how they behave. Funnily enough, this is also true for mathematicians. We don't particularly know how to define them for what they are, but we do know how to make use of their properties. And that's all that really matters here anyway. I would like to recall the 5 assumptions that we had from the last video. Any 2 points can be connected by a straight line segment. Any straight line segment can be extended indefinitely into a straight line. Given any straight line segment, a circle can be drawn having the segment as its radius and one of the endpoints at its center. All right angles are congruent. Congruent just means that they have the same size. And we have finally the parallel postulate, or the parallel assumption, that if 2 lines intersect a third such that the sum of the interior angles on one side is less than 2 right angles, then the 2 lines intersect on that side. To understand what those mean, please refer to my last video, as we would like to start applying these to actual problems. So, what is next? Well, as I said, we'd like to apply these to problems. I'd really like to, if I can avoid just listing definitions, propositions, theorems, and those sorts of things. To do that, what I am going to do is apply the following strategy, is to provide a problem and then tell you the tools that I think are necessary to tackle these problems. What certain words mean, how to apply certain theorems, when certain theorems are applicable, and so on. The main aim is to really get into the details about what problems we can solve with plane geometry, because I think that's the most fun thing to do, to tackle problems. Right, so I've just moved myself out of the way so we can read the problem, which is, given a line segment AB, construct an equilateral triangle. Okay, so what do we need to know here? So first things first, we know what a line segment is. We covered that in the last video. Okay, so let's draw it. Okay, so I won't go over too much last time. We know that we can construct, let's say, this line segment AB here with some finite length. Okay, so applying the axioms that we had, or the assumptions, to be completely rigorous about this, we know that we can do this. We know that points and lines exist, and we know that a single line segment can connect 2 points. Additionally, I think we also need to define what an equilateral triangle is, just in case people don't know. An equilateral triangle is a triangle where all the sides have the same length. Okay, so you might be asking, well then, what do we do from this? Well, what we can do from this is, because of axiom 3, we can draw circles like this, with radius equal to the line segment, with B as its midpoint. Here's the little trick. I'm going to do it again, with A as the midpoint of this next circle, with AB as its radius. So, the midpoints of A and B, the midpoints of this circle here and this circle here, are separated by A and B, which means that the point from A to anywhere on its circle circumference must be A and B, because we've just said that's its radius. Similarly, for this circle here, any point from B to its circumference must be of length AB, because that's its radius by definition. So I've just moved myself out of the way again, because I'd like to introduce now this circle-circle continuity principle. If one circle F, that is this circle here, has one point inside and another point outside of another circle F dash, then the 2 circles intersect in 2 points. I think this is pretty clear, but it's an axiom that we need to define to be rigorous here. So back to this problem. What does this mean for our 2 circles, both with radius length AB? Well, it means that we can apply the circle-circle continuity principle that we've just seen, and we know that these points are the intersection points. These points are on the circumference of the circle. So if I am to draw a line segment from AC and then from C to B, I know that BC has length AB, and I also know that AC has the same length as AB, because from A to B is its radius, and from A to any point on the circumference is also equal to AB, because that is the length of the radius of this circle. C is on this circumference, therefore this line and this line must have equal length. And if you don't believe me, I will hide these things and boom, there we have an equilateral triangle. Okay, and that's how you construct an equilateral triangle. Thank you very much for watching. Hopefully you enjoyed this format a little more. Please tell me down in the comments, like, comment, subscribe. Please become a member of my Patreon to get these videos early. And I will see you all in the next video. Thank you.